Hello students, this is Mr. Allen here. Today we are going to continue our review of Chapter 3, which is Applications of Differentiation. And in particular, we are going to look at the mean value theorem and optimization. So if you see me kind of looking here to the right, I'm basically just checking my notes to see where I'm at. I'm going to try to keep this video to about 15 minutes if at all possible. All right, so MVT and optimization. Our objectives today is to be able to understand and use the mean value theorem and to be able to solve applied minimum and maximum problems. So the objectives are very light today. So let's just go ahead and get started. So the mean value theorem, which is, well, let's talk about Rolle's theorem. Rolle's theorem is when the slope is 0. The mean value theorem is more general than Rolle's theorem, and the mean value theorem says the following. If f is a continuous function that on the closed interval from a to b, and if it's differentiable on the open interval from a to b, then there exists some value c on that open interval a to b such that f prime of c is equal to f of b minus f of a over b minus a. So when you look at this, you should kind of notice that we have something that looks like the slope formula here. This is the slope formula that you learned about way back in Algebra 1. And then over here on the left-hand side of the equation, you're seeing basically the slope of a tangent line, or the derivative might be a better way of saying that, but that's the derivative. So if we look at this next slide, and by the way, this is the key equation, and these are the requirements. If we look at this next slide, we have this curve f of x that's drawn in black. And you'll notice that we're starting at endpoints. We're starting with x is equal to a. We're going up to x equaling b. We're only considering that piece of the curve. And we find that the slope, that's the slope of the secant line. Let's just say that slope is, I'm going to call it m sub s. Let's say that's 1/2. The mean value theorem guarantees us that there has to be some value c between a and b such that the slope of the tangent line, is also equal to that 1/2. So in this case, we would say that the slope, I'll call it m sub t, is also 1/2. Now, keep in mind that this theorem is an existence theorem. It just tells us that there exists a value c. It does not tell us where c is located. You would have to determine that through other methods. And it also doesn't tell us how many values of c there are. There could be more than one. In terms of rates of change, the mean value theorem implies that there must be a point on the open interval where the instantaneous rate of change, aka the derivative, is equal to the average rate of change. So there's several different interpretations of this. So let's look at our example, and I'm only going to do one example of the mean value theorem. So we've got our function f of x, and we're asked to find the values of c, all values of c, on the open interval from 1 to 3, where f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. So the first thing you would need to do is you would want to figure out what f of 4 is. Well, it turns out that f of 4 is 4, and it turns out that f of 1 is 1. Now, I'm not going to go through and explain to you how to do that, but if you didn't know what f of 4 was, you would plug 4 into the function and you'll see that it is indeed 4. Okay? So what I can then do is, based on that information, I can make this right-hand side be equal to 4 minus 1 over 4 minus 1, because I just substituted these values in for f of 4 and f of 1, which tells us that the slope of the secant line, if you will, the slope of the secant line is 1. So what we're trying to figure out then is, when is f prime of c equal to 1? That's the question we've got to figure out. Well, in order to figure out that answer, we've got to figure out what f prime is. Now, to figure out what f prime is, I'm going to rewrite our function here. F is equal to 5 minus 4x to the negative 1. So f prime is going to be equal to 0. and I'm going to cheat here a little bit. I just want to make sure that I get this correct. So then we're going to do the negative. We're bringing down the negative exponent of 1, so that's going to become plus 4, and then x to the negative 2. And so we could rewrite this then as 4 over x squared. That's what f prime is. So again, what I'm trying to do is I am trying to figure out what value is 4 over x squared. What values of x is this true for? So this is a pretty simple equation. We can solve this, and you'll very quickly see that x is equal to plus or minus 2. Now, you might be tempted to say that the answer is plus or minus 2, but remember, we've restricted ourselves to the interval 0 to, from 1 to 4, so it can't be negative. So our final answer here is C is equal to 2. So I claim that f prime of 2 is equal to 1, and my guess is I hope that you can figure out when you plug that in there that that is indeed true. So that is the mean value theorem example. So let's go ahead and look here at this picture. This picture just shows us what we just did graphically if you wanted to see it. The black curve is the function itself. You'll notice that they give us the secant line slope down here. The secant line slope here is 1. And then the tangent line slope there is also going to be 1. And it turns out to be when x is equal to 2. So we did figure out the correct answer. And I got a typo here. This should be solution for 1, because this was example 1. I'm sorry about that. Here's another form for the mean value theorem. It's a very easy translation. If you have f prime of C is equal to f of B minus f of A over B minus A, you can probably figure out how to get from that to that. It's a very easy algebra problem, but this is just an alternative form that you might see. You don't have to have that memorized. It might be related to something that we'll talk more about later this semester, though. Okay, so let's go ahead and talk about optimization problems. Here's a table with steps. I'm not going to read through these. These are in your notes from last year. If you want to look at them in the textbook, you can. I'm just going to go ahead and do a couple of examples. So here's our second example of the day, but the first optimization problem. So we've got this cylindrical can, and we know that its capacity here's 1,000 cubic centimeters. We know that the top and the bottom are made of some material that costs 5 cents per square centimeter. The sides are made with material that's 3 cents per square centimeter. We were trying to find the dimensions that will minimize the cost, which kind of makes sense. If I'm making a product and I want it to hold 1,000 cubic centimeters, I want to try to minimize how much it costs me to make those cylinders, those cans. So a couple of things that we need to keep in mind is the surface area formula for a cylinder, which is, I think, 2 pi r squared plus 2 pi r h. Now, this is something that I just know. If you didn't know that, you would need to look that up. We also know that the volume formula is pi r squared h. So we have these two formulas. These are known formulas. They're going to be helpful for us, because what we need to do now is we need to figure out what is it that we're trying to do in this problem. This is an optimization problem. What are we trying to optimize? We're trying to minimize the cost. We're trying to minimize the cost. So that means I've got to write some sort of cost function. So what is my cost function going to be? Well, the cost function, is that based on the volume or the surface area? Well, it's the surface area. So I'm going to have to do this same thing that I used just a second ago. So I'm going to have to use this 2 pi r squared plus, and then this 2 pi 8 or RH. But now we've got to add some information to it. I'm going to do this in red. Notice that they're telling us the cost of the top and the bottom is 5 cents per square centimeter. So I'm going to put 0.05 here in front of the 2. And you can probably guess what I'm going to put here for the sides. So remember, this was the top, this is the top and the bottom, and then this is the lateral surface area. So I'm going to put 0.03 in here. This is a 5, by the way, sorry. So this is our cost function, but it's got two variables. Pi, remember, pi is not a variable, but it's got an R and an H. I don't like the H because if I've got two variables, you guys haven't taken multivariable calculus, which you'll take maybe someday, but not yet. So what we can do here, here's the other little trick that's very common in these types of problems, is we're actually going to use this equation right here. In fact, I'm going to argue that that volume has to be 1,000. It doesn't change because they gave us that in the problem. And so what that tells us is that H is equal to 1,000 over pi r squared. Now I can plug that into here. Now I'm kind of taking a little bit of a liberty here, but I'm telling you that the cost function is now going to be in terms of one variable. I'm going to cheat here just a little bit. I'm going to let you figure out all the simplification here, but it's going to give you pi over 10 r squared plus 60 over r. This is after you simplify all the stuff that I've done there. Okay. Now I spent some time on this problem, not a lot of time, but we've done some work. I have not done any calculus yet. So now I've got my cost function. What am I trying to do with my cost function? I'm trying to minimize it. So this is the function that I'm going to minimize. So in the next slide, now what we're going to have to do is we got to try to minimize this function, which again is pi over 10 r squared plus 60 over r. Now you'd have to, I'm going to again assume you know how to do this, but we're going to have to do the derivative of this, which hopefully isn't going to seem like much of a problem here. It's going to be pi over 5r and then minus minus 60 over r squared. That's a 60. So this is the derivative. And the reason we need that is that's how we figure out where maxes and mins are. But in order to figure out maxes and mins, we got to figure out what our critical numbers are. And remember, critical numbers are where this derivative is equal to 0 or d and e. Now, I'm going to throw out the d and e on this example immediately because if I figure out where that's equal to d and e, well, that'd be when r is 0. That means the radius is 0, which means it's not a cylinder. So I'm not going to worry about d and e. I just need to figure out when this is equal to 0. So let's go ahead and keep going in green. So this is going to be pi over 5r equals 60 over r squared. Actually, I guess I should maybe explain a little bit what I'm doing there. We want to know when that's equal to 0, right? So if I just take this negative 60r squared and move it over the other side, I get this equation, correct? So now we can cross multiply here. You're going to end up getting, let me go back to green, r cubed over, equals 300 over pi. And then, of course, you got to do the cubic root of that. So r is equal to the cubic root of 300 over pi. It's not letting me write this here, guys. This is an over pi here. There we go. Sorry. By the way, that decimal is approximately 4.571, and this is centimeters. So I'm telling you right now, you could check that. You could see based on this that C prime is going to change sign from negative, let me write negative to positive at this value. That makes it a minimum. Okay, now that we have r, this is r, which by the way, this is the exact answer over here, the cubic root of 300 over pi. And by the way, all of that's into the square root. Then the h, you would just do a substitution, and I'm going to just go to 3 decimal places on this one as well, is 15.236 centimeters. Okay, so these are the dimensions of this can to minimize the cost. All right. Let's go ahead and finish up with this last example here, which is maximizing the area. It says a rectangle is inscribed in a semicircle of radius 2. Find the dimensions of the rectangle. So this one we're trying to maximize the area. So I'm going to just draw a little picture, and we'll just leave it in green. I'm going to try to make a semicircle. That's not a great circle, but we're going to go with that. We're going to let this be the x-axis. We're going to let this be the y-axis. And then I'm going to draw a rectangle, if I can, maybe in here. Okay, good. So again, my picture is not perfect, but it's going to work. So we're going to pretend that this is a perfectly drawn semicircle, and we know that the radius here is 2, right? So I could argue, I wish I would have done that in green. We could argue then that this circle has the formula x squared plus y squared equals 4 based on my drawing, right? In other words, well, we'll leave it at that. We're going to use that in a minute. Okay, so far so good. Now, let's just go ahead and say that this distance right here is x, because it could vary. It could go from zero, it can't be 0, but it could go from 0 all the way up to 2, right? Because the radius is 2. So x has to be between 0 and 2, but it's variable. Now, if that side is x, well, guess what? What's this length over here going to be? Well, if the right side is x, and I made my rectangle, my circle centered right there, this side over here is also x. So now the question I have, and it's an easy one to answer, is what's this total distance, or this, by the way, we're talking about a rectangle. We're trying to maximize the area of a rectangle. And hopefully you guys know that the area of a rectangle is, I'm going to call it base times height. You might call it length times width. That's the same thing, right? So what's that base length? Well, what's x plus x? That's going to be 2x. So that's going to be 2x. An x plus another x is 2x. Now, how about the height? What is the height going to be? Let's do that in orange. How am I going to find the height of that rectangle? Well, it's just y, whatever y is. So how do I figure out what y is? Well, we're just going to use this equation right here. Now, I'm going to kind of skip some steps, but you could solve for y by subtracting x squared over and then doing the square root. So then this would be the square root of 4 minus x squared. That's what y is. This is y. So the base of the rectangle is 2x. The height of the rectangle is the square root of 4 minus x squared. Those are our restrictions. And we're trying to, and by the way, you'll notice this is all in one variable. That's why I wanted to get rid of the y. So now I can go ahead and solve this. So we want to maximize this function, and I'm going to call it area in terms of x is equal to 2x times the square root of 4 minus x squared. Now, in order to find that derivative, you can use your graphic calculator. I'm going to go ahead and I'm going to cheat just a little bit. And I'm going to cheat because I've already worked this out. You'd need to do the product rule and the chain rule, and then you'd need to clean it up. Turns out that the derivative here is negative 4 times the quantity x squared minus 2 all over the square root of 4 minus x squared. That's our derivative. We want to figure out when that is equal to 0 or d and e. And in this case, I think we just want to focus on when it's going to be 0, which you could probably look at it right now and guess what it is. D and E, again, is not going to help us. To make this D and E, what would x have to be? Well, x would have to be 2. If x is 2, then basically the height of this rectangle would be a 0. And if it's 0, it's not a rectangle. So we're going to, again, disregard this. We're only going to worry about it when being 0. And so what I'm essentially asking is when is negative 4, quantity x squared minus 2, when is that equal to 0? Well, hopefully you can look at that and just tell that x is going to be the square root of 2 is when that would be 0. Now, you could put plus or minus, but remember, we're talking about a measurement. So you're not going to have, you can't tell me that, the length of a side is negative square root of 2. You could tell me the coordinates is negative square root of 2, but not the length. So I know what x is. So what would y be? Well, y is defined right up here. This is what y is. This is y. So if we plug that in there, square root of 2 squared would be what? 2. So that's the square root of 2 as well. Now here's where we got to be very careful. It says find the dimensions. Now you might be tempted to say square root of 2, square root of 2, but what is the dimensions of the base of this? Well, it's not just x, there's 2 x's. So I'm going to go ahead and finish this up. So to maximize the area, I'm going to let the base equal 2 times the square root of 2, or 2 radical 2. And then the height is going to be just the square root of 2. I don't know if I gave you units here. No, no units. And so that's it. Hope that makes sense. And I'm going to stop the video here. Hopefully that's close to 15 minutes.